Good morning, everyone. Happy to see so many happy faces here in the room for our seminar today. The talk of today will be given by Jake. Jake did his bachelor master studies in Australia, Macquarie University, and he's currently doing I think officially dual PhD between KU Leuven and Macquarie University, but I just learned from Jake that in Australia people are privileged. They don't do defense at all. So Jake will have the opportunity to experience the internal and public defense here at KU Leuven. I don't know anything about Jake's hobbies, except that he likes participating in quiz and winning the one from a couple of weeks ago. Congratulations, Jake. So that's an achievement. Today, Jake will talk about Marvel. It's a very generic title, as you can see, but I have a suspicion this is going to be about instrumentation and maybe a little bit of the science exploitation. I don't know, we'll see. So the floor is yours, Jake.
Thank you, Andrew. Can everyone hear me all right with this? Okay. So yes, today I want to talk to you about Marvel. In fact, not this one. If anyone's here for this talk, then I'm sorry to disappoint you. Try that again. Today, I want to talk to you about Marvel. Also not this one, even though it looks suspiciously similar, if you're familiar with our Marvel. This is, in fact, a previous instrument, part of the Sloan Digital Sky Survey. Okay, third time lucky. Today, I want to talk to you about Marvel. Okay, that's a bit more familiar. So this is, as I'm sure most of you are at least somewhat aware, this is a new addition to the Mercator observatory. The Mercator telescope is right there, and Marvel, these lovely four domes, are right next door. So today, I'll introduce or reintroduce you to the facility Marvel, a little bit of a refresher on radial velocity measurements and how these are made, what we actually measure, what's the relevant scale, precision that we're talking about here. I'll talk about the ambitious goals of the Marvel facility and in particular how these have driven the instrument design, the whole facility design. So I'll basically answer the question, why does every radial velocity spectrometer look very similar? So we'll go through that. And then at the end, I'll get to some of the future challenges because, well, we're sort of in the middle of the project now, yet to begin commissioning of the instruments and most of the facility. So there's still a lot of work ahead. Okay, so Marvel, like I said, is at the Mercator Observatory. It will be a dedicated robotic, sort of automated facility for radial velocity measurements. So it's designed for survey work. That's why you see 4 telescopes. You can measure 4 different stars at the same time, going through a survey very quickly like this. Its primary goal is sort of target vetting and target follow-up of stars that have been measured with space-based photometry systems, so that the TESS mission, the upcoming PLATO mission. So inside these 4 domes, we have 4 telescopes, no surprises there. And underneath me in this picture, in the building that's just out of frame, we have 1 high-resolution spectrograph. So this is what the telescopes look like. This is the concept diagram of the thing. So these are indeed 80-centimeter telescopes. They're small for observatory standards. They're large for amateur standards, but in fact these are off-the-shelf items. If you were a very rich and very keen amateur observer, you could have this in your backyard. These are coupled to the spectrograph by optical fiber, these red links. There's a 5th fiber which comes from wavelength calibration source. That's very important, and I'll get to that later. So, radial velocity measurements, I'm sure you've all come across these before. So I'll talk about radial velocity, RV, in the middle of MARVEL, and Doppler spectroscopy. These are all kind of synonymous. So it's the measurement of red and blue shifts of spectral features over time. So here we have a star in the center and some unseen, unresolved companion orbiting around. These two, in fact, orbit a common center of mass of the system. And so as this planet or other body orbits around, the star makes a small orbit. And you see here, very exaggerated, but you see a red and blue shift of spectral features. In the field, if we talk about precision RV, we're talking, well, maybe below 10 meters per second precision. And if we talk about extreme precision RV, this is 1 meter per second. This is walking pace. You're measuring the velocity of a star down to this speed. So why do we want a dedicated facility like MARVEL for this kind of work? Well, there's a whole bunch of reasons to this, but it really comes down to the instruments that are capable of reaching precision that we're talking about are very expensive, very specialized. They're usually at very large observatories. You therefore would have to compete with the entire astronomical community for time, observing time on these facilities. For follow-up of something like PLATO, which is expected to yield several thousand candidates that need sort of lots of follow-up points. Here I say 30 plus, we're talking 30 to 100 epochs of observation. 4,000 targets with this many follow-ups is sort of impractical if you have to compete for this time. So this is why a dedicated facility. Okay, so I talked about following up tests and PLATO observations. These two are doing photometry. So what does the combination of transit photometry and radial velocities give us? Well, from transits you get the planet's radius, or its radius as a fraction of this star's radius. You get the orbital period very well. You also know that the system is basically inclined 90 degrees, otherwise it would not transit in front of the star. From RV, we then get the mass of this planet. If you don't know the inclination, you get an estimate of the mass, you get a minimum mass of the planet. But here we really get the mass almost directly. From the mass and the radius, we then can work out the bulk density of this thing. So this can distinguish between different types of planets. We talk about super Earths, sub-Neptunes. If you're more interested in that, I referred you to Carl Stubb's talk from 3 weeks ago. It was very good. So the main goal of MARVEL is radial velocity precision of 1 meter per second, as I said. Why is that hard? Well, a Doppler shift, so this shift up here, extremely exaggerated, Doppler shift of 1 meter per second corresponds to the shift of the spectrum on the detector of 1,000th of a single pixel. So this is why this is a difficult measurement. This has a number of implications for the instrument design, the facility design. So I'll talk about those now. The way I see it, there's these 5 things that come out of that one top-level science goal. Well, 4 things plus 1, which I'll talk about separately. To get there, we need high spectral resolution. We need broad wavelength coverage. We need extreme stability of the entire system. We need impeccable wavelength calibration. And for Marvel more than other facilities, we need high throughput for this. So I'll talk about each of these in turn. Now, in different fields, high resolution can mean different things. Here, for RV work, we talk about high resolution at the point where a spectral line is resolved, where you can start to measure the position of this line with some sort of surety. You can see that resolution 10,000, 20,000, this is still not resolved. Anything above 40,000 and you start to be able to do this. But we might want even higher spectral resolution. We actually care not just about the positions of lines, but also their shapes. And so you can see with this green curve here, you might not be able to determine anything about this line's shape, but with the higher resolution ones, you can. So typically in RV instruments, this gets bumped as a requirement to twice this minimum resolution to resolution of about 80,000. To achieve this, and I've sort of got these target bullseyes here to indicate what then becomes the requirements of the instrument. To achieve this, we have to use a grating as our dispersive element. Now, this might seem like the most basic requirement, and indeed it is. They get more involved as we go on. Okay, broad wavelength coverage, I said. Why is this? So the RV information is in the position of all of our spectral lines. If you use more lines, you get higher precision. And this is basically what it comes down to. This pushes RV facilities to two things. One, observe cooler stars with more lines, okay. And two, have a broader wavelength coverage. You're really just capturing more spectral lines in the extra parts of the spectrum that you can cover. So this is sort of, where do you draw that line? It should be broad enough to cover sufficiently many spectral lines, but where is that? We also care about specific parts of the spectrum more than others. So there's some parts of the spectrum, some individual spectral lines that act as indicators of stellar surface activity. These ones we care about extremely much because surface activity, like a sunspot here, affects the distribution of radial velocities by selectively blocking out part of the starlight. Down here I've got an RV map of the surface of the sun. You can see part of it, the part that's rotating towards us, is blue shifted, and the part that's rotating away from us is red shifted. If you selectively block part of that out, you get this systematic bias in your RV measurement, and in some cases this looks exactly like the signal of a planet. So you really want to know, is there stellar activity? How do I overcome this and get beyond it? So we care about these particular stellar activity indicators. There's other parts of the spectrum we care about less. So any part that's contaminated by the Earth's atmosphere, for instance, is less usable for RV work, and so those pushing to those parts of the spectrum, so further into the near infrared, for instance, is less important. So the way we defined it for Marvel was we took these particular activity indicators, the calcium H and K lines in the near UV, and the calcium near infrared triplet in the near infrared, and we wanted to capture all of these and everything in between. So that's how we came up with this number. We pushed a bit further red because, well, for several reasons, but because it basically didn't come with any extra complications. Okay, the next point was stability. Extreme stability of an RV spectrometer, and in fact, everything around it, so the way you inject light into the system, is really critical. It's not just stability during an observation, but in between observations that can be a year apart. You really want nothing to have changed in your instrument at the level that you care about, which again is about 1,000th of a single pixel during this time. Or if it does, you want to have tracked this, you know what has changed, how it's changed, and how to accommodate for this, which I'll get to later. So, stability requirement pushes us to two things. The instrument should be held under vacuum. This insulates it from any changes in the outside world. In fact, for Marvel, we sort of nest everything in 3 or 4 layers of ever more stable rooms before we get to this vacuum vessel that it's in. The other thing that this pushes us towards, and every RV facility, is using optical fibers to couple light into the instrument. So this allows you to put your spectrograph not right next to the telescope. So with the other option is feeding it with a slit, and then this thing has to be mounted on the side of the telescope. Optical fibers allow us to put this in a dedicated space that's more well controlled. Okay, I also said we need impeccable wavelength calibration. I just like the word impeccable, okay? That has no scientific meaning, but I just like it. So the wavelength calibration of an instrument like this, well, we use this as a ruler against which the spectrum is moving. We need wavelength calibration to know which pixel corresponds to which wavelength to a very high degree of accuracy. But with the previous requirements on high resolution, and in particular, very broad wavelength coverage, this becomes a bit less trivial. So finding a good wavelength calibrator for a system like this is a tricky task. And now I'll take a short detour about wavelength calibrators in particular. So how have people done this historically, was what I was thinking here. So the first mention I could find in literature about wavelength calibration aiming for high precision was actually using the atmospheric absorption lines that I said before we don't care about in our spectrum. So in fact, these, if anyone has observed with Mercator, as I'm sure most of the room has, you will maybe recognize some patterns here. Now, this is not a spectrum from Mercator, but these patterns are imprinted on every high-resolution spectrum in the same way. So you see these all the time. These are in fact imprinted on the last few kilometers of travel path of the light from distant stars by the atmosphere. And because these are always more or less the same, you can use these to measure the shift of the stellar spectrum against. But they only appear in certain parts of the spectrum. They often appear in clumps, like you see here, and then, well, a lot of this is completely clear of these lines. They also, like I said, contaminate these parts of the spectrum, so they're far from an ideal calibration source, but this is a historical one. Okay, the next step is using the same principle, but doing it in a more controlled way. So here, instead of waiting for the atmosphere to imprint reference lines on a spectrum, we can use a small cell full of a gas of our choice and pass starlight through this on its way to the spectrograph. So this still is used, in fact, for many instruments with molecular iodine in this cell here, and this is then temperature controlled so that it's trustworthy, it's stable over time. This imprints a very dense forest of spectral lines, reference lines, on the stellar spectrum, but only within a small range of the spectrum, so 500 to 600 nanometers. This part of your spectrum, well, is also then contaminated by this, so you lose stellar information, but you gain this reference information. So this too, in my book, doesn't quite meet the tasks that we're talking about here, but in fact, the RV precision that is possible to get with this, if everything else is extremely good as well, is down to about 15 meters per second. So it's not quite down to the level of precision that we hope to achieve with Marvel, but still interesting. Okay, the next step, instead of using gas absorption, is to use gas emission. So this is now much more common than the absorption cell technique. And typically, we're using holocathode lamps of thorium-argon for visible light, uranium neon for near-infrared. So this here is, you see a spectrum, a raw spectrum on the detector of a thorium-argon lamp. You see indeed many spectral lines. The wavelength range we're talking about here is maybe 850 down to maybe 400 nanometers here. So this is basically the full range that we care about. And indeed you see several thousand, at a guess, several thousand spectral lines. But there are some problems with this too. Well, first, you see some that appear in clumps, these sort of streaky ones. These then are blended lines, and they can't be used for very high precision measurements. You also see a huge variety in brightness of lines. So, indeed, up here, this sort of constellation of very bright lines, in fact, they're bright to the point of full saturation of this particular frame. These are coming from argon, which is the fill gas of this holocathode lamp. The rest are thorium, but indeed there you also get a huge variation in brightness. So this is getting there, but I would say still not ideal. With this kind of cell, you can achieve precision down to a few meters per second, and people have done this. So what is an ideal calibrator? Well, you would have first spectral lines that are of equal brightness. These lines should be evenly but densely spaced across the full instrument bandpass. These lines should be also spectrally narrow, so spectrally unresolved in the instrument. They should also be stable, of course, in wavelength, not changing their position in that axis. So the system, well, should also be reliable. It shouldn't require interventions and so on. And is it too much to ask that this thing is cheap? Turns out, yes, it is too much to ask. So there's two kind of avenues to this ideal calibrator. Laser frequency combs, which is more like a commercial product that's possible to buy if you're incredibly rich, and something that's a bit more DIY. So laser frequency combs, they indeed produce this ideal calibration spectrum of dense, evenly spaced, equal brightness lines across the entire bandpass, maybe not so much down at the very bluest end of our wavelength range. But these are also very complex, optical, mechanical, electrical systems. They often require maintenance and sort of in-person maintenance. One guy from this one company flies out to your observatory and tweaks one thing to fix it. They're also very expensive. I put here $6 signs. Now, maybe this is the exponent in the price, something like that. Okay, the other option is Fabry-Perot etalons. Now here the price is, this is not the exponent in the price, so forget that. Okay, so these are optical cavities. So inside this structure is two mirrors with very high reflection surface facing each other. So just like when you step in an elevator and you look left and right, you see a large number of images of you. Inside this system, light going through sees itself many times, and it interferes and allows only light at very narrow wavelengths to then pass through out the output of this system. So unlike the laser frequency comb, this is a passive optical system. It's really just sitting there, you shine light through it, you get this spectrum. The range of this spectrum depends on the reflectivity of the mirrors, which is wavelength dependent. It also depends on what white light you illuminate this with. And indeed, quite a bit cheaper than a laser frequency comb. But, there's always a but with these things. The true wavelength of any single one of these lines is not known. We have no external reference by itself. So we need a wavelength calibrator for our wavelength calibrator. So we measure a single line of this spectrum against a known transition that's known very well. In the case of this system here, we use that transition in rubidium to reference this against. There's a small star here, which we'll maybe get to at the end. So with the active monitoring system, this whole system, the etalon system gets quite a bit more complicated, and I added $2 more signs on there. Okay, but the calibration system, it really is important to these types of instruments. A really good calibration system is not just for wavelength calibration. You use it, sure, for wavelength calibration, but you also use it to track any drifts of the instrument in between these times that you're calibrating the wavelength. So if you take a calibration spectrum at the start and end of the night, maybe in the middle as well, but you also take a reference spectrum simultaneously with every exposure, you can then track how this has drifted from the start to the end of the night. It's not flat, it's not always linear, this is sort of shifting. So this becomes another target for our system, for Marvel, to have a simultaneous reference fiber as a fifth input to the spectrograph. Very important. Okay, I also said high throughput. Now this is more important for Marvel than other facilities at, for instance, larger telescopes. Because the Marvel telescopes are only 80 centimeters, this puts a limit on how dim a star we can observe with this. So the target limiting magnitude for the system is sort of a V magnitude of 11. This is in concert with the requirement of 1 meter per second precision within 1 hour exposure. So that's what we're talking about. But if there's anywhere in the system that we can gain in efficiency, in throughput, that allows us to push to dimmer targets, which is more of a limit for Marvel than on, for instance, a 4-meter telescope. So we also care about high throughput. So this target here, we also want to maximize efficiency. This means high-performance coatings on optics, reflective or anti-reflective, high transmission glass in lenses, and the fewest possible number of surfaces. So at every surface, you lose a tiny bit of light. This all adds up. So all of these requirements, when you consider everything together, push towards a single common architecture of instrument, which perhaps it's not surprising then that most RV facilities look similar, at least the spectrograph looks more or less the same. It's this here, and I'm aware that there's quite a bit of jargon in this, so I'm going to go through that too. It's a white pupil relay cross-dispersed Echelle spectrograph. But what does that mean? Echelle is the grating that we use. This is the main dispersing element in the spectrograph. It's reflective, seen at a very high incidence angle. So here, this one is, I think, 80 degrees. Here you see a picture of me reflected under this steep angle. So this is because the steps of this grating surface are oriented in this picture towards me, towards the camera. What does cross-dispersed mean? Well, this grating produces diffraction orders, many diffraction orders at sort of, this splits the spectrum across maybe 50, 60 different orders in parallel. But these are all sort of overlapping. So we need to either filter them out, which means throwing away parts of your spectrum, which we don't want to do, or spatially separate these. So we put another disperser in the orthogonal direction, which in Marvel is this large prism. This then separates the spectrum, these spectral orders, to fill the detector. And lastly, what is a white pupil relay? Well, this is kind of this looking thing here. So it's a system that relays or images one position in that system onto another position. In our case, we put the grating at one of these pupils that we relay, and we image that onto the other side, the output side, where we put the cross-disperser prism, where we put the first lens of the camera imaging system. This keeps all of the optics small. It means that you can get high transmission everything because it's not prohibitively large. And this white pupil relay is common across basically all modern radial velocity facilities. So everything, that's why everything kind of looks similar to this. So then we get to Marvel. And yes, this is the spectrograph Marvel here. So there was significant design heritage that comes from Hermes at Mercator, which most people are familiar with. Also from a spectrograph not pronounced like it looks, pronounced NUID. It's a white pupil relay that also folds the beam around. This keeps the entire instrument volume small, meaning that you can put it inside a vacuum vessel and temperature control it more easily. We covered the spectrum from 380 to 950 nanometers in a single pass on a single very large detector. It's fiber fed, 4 input fibers from telescopes and 1 from the calibration system. These fibers projected on sky subtend an angle of 2.4 arc seconds, which is well matched to seeing conditions at La Palma. We have two modes of resolution. So there's one that meets the double the minimum requirement at 90,000. We also have an ultra-high resolution mode, which pushes it even further for nights of very good seeing, perhaps. And we'll have a wavelength calibration system built around one of these Fabry-Perot etalons. So this is what the spectrum looks like. Here I've marked the dispersion direction, horizontal, cross-dispersion direction, vertical here. This full large detector captures almost the entire spectral range. We have a couple of bits of where it doesn't quite cover for 4 telescope fibers and 1 calibration fiber. Here's the layout of the spectrum. So you see I've circled the calcium near-infrared triplet and the calcium H and K activity indicators in this. So this is really where our spectrum spans. Any redder and you run into detector problems. You run into loss of efficiency for the CCD, and this really puts a stop. And any bluer than, we go to about 390, any bluer than this and you start to run into problems with glass transmission, you end up with basically 3 or 4 types of glass that you're able to use and no more. So it becomes difficult to design an instrument for bluer than this. This is what that detector looks like. I'm holding it, just kidding. This is a, well, if it wasn't broken when I picked it up, it was broken when I put it down. This is something of the same size as our detector. This is the largest commercial CCD that is possible to buy. This is 10,000 by 10,000 pixels. This whole system here is the sort of life support system for the detector, the CCD itself, and this is being delivered to us. It's sort of subcontracted out to UK ATC. The system efficiency, the throughput of this system, leads us to this sort of limiting magnitude if we want to achieve an RV precision of 1 meter per second in 1 hour. That's this curve here, 1 hour. So this is dependent on spectral type, really on surface temperature. Like I said, cooler stars, you reach this 1 hour, you actually reach to a deeper limiting magnitude. Okay, lastly, the future challenges of this system. So while a lot has happened for Marvel, there's still some of the most challenging work is still yet to come within the next year and beyond. So achieving this precision target is by no means a given. You can design all of this and then one thing can stop you from achieving that. So you sort of have to beat down every single pillar in the noise floor to achieve that. So these are the largest challenges I see, or 4 that I chose for the context of this talk, and I'll talk about each of them briefly. So the illumination stability of an instrument like this is really critical. None of our optics are perfect. In fact, a few of these are far, far, far from perfect than where we would really ideally like them. And so any changing illumination of these optics, if you shine more light on the top part of our grating than the bottom, then the image at the detector shifts by much more than the equivalent of 1 meter per second. So we better be absolutely sure that we illuminate the instrument evenly, stably over a long period of time. Because this is fed with optical fibers, we then have to understand these fibers, their behavior, very, very well. So there's a few tricks that can be played to increase this performance of fibers, which, well, I won't go into them now, but there are ways out of this. So the environmental stability, maybe I'm less concerned about this one, but it's also very critical to get right. So the spectrograph is in a vacuum vessel which is roughly 2 by 1.5 by 1 meters volume. This needs to remain stable at, or well below, let's say, the level of 1 meter per second, which is about 13 nanometers of detector shift. So the whole thing should be stable at that level. At 13 nanometers, it becomes, to me, very difficult to trust any kind of simulation of a system. And so we really try and do just the absolute best that we can. We're aiming for 1 millikelvin, so 1,000th of 1 degree Celsius of deviation during operation. And we think we can get there because this plot here shows the Hermes internal temperature measured at the grating. This blue line is that temperature. The blue shaded region is plus minus 10 millikelvin. So it's a factor 10 worse, but Hermes is not inside a vacuum vessel. So we think with this extra level we can improve this performance by that factor 10 that's required. So the wavelength calibration, the Etalon system that we use, if you measured that, the position of its reference lines against the position of the reference lines of a laser frequency comb, which are all known wavelengths, then you see drifts. You see this curve here is one that I've generated from an Etalon at the Keck Planet Finder in Hawaii. So you see a bulk drift of, I don't know if you can read this, a bit more than 5 centimeters per second per day in radial velocity space. So after 20 days, then you're past this 1 meter per second point. But more than just the bulk drift, you see chromatic drift. You see that these reference peaks are moving in one direction in the red and in another direction in the blue. And in fact, we expect that there's quite some oscillation between this. So this becomes tricky for Marvel in particular because we do not have a laser frequency comb against which we can measure this. So we'll be using the Etalon really blind. Well, we use it with the knowledge that it is drifting. So this is a big challenge to overcome as well. And lastly, I think stellar activity is a huge limiter to the level of RV precision you can achieve on a real star. Or let's say it limits the size of a planet that you can detect because the stellar activity suddenly dominates the RV landscape. So in this plot you see, I've labeled it here, this line is sort of representing instrument improvement. This is improvement in stability, in wavelength calibration, in everything I've talked about. And for a long time, this was seeing good results. Every following year would push to smaller RV, detected RV signals from planets. And then we hit this sort of floor here at about, well, here I've marked it as about 0.5 meter per second. This, in the field, everyone is saying that this is really just stellar activity. We don't understand these stars well enough to overcome this. And so this also is a big challenge to really achieving what we want to achieve. And I think that's it. I know Kastub also played this video, but I think it's so good it's worth playing again. Maybe? What does that say? Okay, maybe it's not worth playing again. It's the construction time-lapse of the Marvel domes and spectrograph room, but, well, you can ask Wim very nicely and he'll show you this. But with that, I thank you for your attention.
Thanks, Jake, for this technical but very well explained talk, at least for me. Now we have time for questions.
Hi, Jake. Marvelous talk, if I may say. So the design is quite close to the one that you have for the Mercator from the picture that you were showing. So I was wondering if you were able to improve the throughput compared to the design of the Mercator. Do you have any new coating, new fibers?
I think there's actually a lot that's different in this design here from the Hermes design. In Hermes, this mirror is actually two mirrors. These are used independently and independently focused. So here we were maybe able to get a much better coating on this because it was a single mirror. The camera is also, in spectrograph lingo, we call, somewhat confusing, we call the camera these lenses and not the detector. The detector is a detector, it's not a camera. So here, the camera is quite a bit different as well. In Hermes, I think there's an extra couple of surfaces there, and at every surface, like I said, you lose maybe 1–2% of light, depending on wavelength. So here we were able to maybe save a little bit. The other big difference, because Hermes is on a larger telescope, you then need a larger fiber to collect starlight. And that means in Hermes, the fiber first goes through an image slicer to break this single fiber into two images, forming the spectrograph slit. And that slicer sort of costs a bit in transmission sense. So I think because we don't have to use a slicer because we have smaller telescopes, we then save a bit there as well.
Do you have an estimate of the throughput?
I had it somewhere here, didn't I? This is quite optimistic. There's a couple things that are missing from this, but this shows first the blue curve is 3 reflections from the telescope mirrors. Okay, then the optics in what we call the front end. So this is all the guiding and imaging, re-imaging, focal reduction optics here to couple into the fiber. The green curve is loss at the fiber aperture, fiber transmission for 30 meters of fiber or something. I think it's less. Then spectrograph optics, then detector, and then finally, because of the structure of the shell orders down the bottom, this here ends up at about 30%, which would be incredibly high for an instrument like this. So the typical value is maybe more like 10% or less. If we can reach 20%, that would be incredible. And I think reasonably within reach. It's difficult to say though until we finally get the thing on sky and measure against a star that we know really well.
Okay, thank you.
Thank you for the great talk. Can you go to slide 43 with the shifts? Yeah. So you talk about this median drift, but that would be something that's then compared with like the rubidium calibration system. So is it correct that it's only like between the different wavelength shift that you would get, or also the medium shift?
We get both. So here, this is measured really against the absolute standard of the laser frequency comb, which from everything that VELocities, the people who make this, from everything they tell us is trustworthy no matter what. The way the laser comb works is it's referenced to like the SI definition of a second via GPS. So it's really just generating these peaks at exact wavelengths. So here, yeah, we will also see this bulk shift, but that's something that's a bit more calibratable. The chromatic drift is much more what people are worried about. Anyone that's using an Etalon as their only calibrator needs to worry about this. Yeah.
Okay, thank you.
And I think it's interesting. It's somewhat paradoxical. You have a cavity that's defined by these two mirrors that is getting shorter at one wavelength. Like for one wavelength of light, this cavity is shrinking. And for another wavelength, this cavity is expanding. So in fact, it's not physically shrinking and expanding. It's, as seen by those wavelengths of light, the phase delay that accumulates is variable. So it's in the optical coatings of these mirrors.
There is still time.
Jake, I have a question. If you go observing with Mercator, the most used, let's say, instrument is the exposure time meter, because that allows you to increase or decrease the exposure depending on how much photons enter the spectrograph. But it's also important for the radial velocity because you want to have the mid exposure time within your, so the mid exposure time is not the same as the mid exposure photon time, because it depends on how the throughput is varying throughout the exposure. How is that solved in Marvel?
Yeah, so we'll also have an exposure meter. Looking at the grating from this direction, most of the light is reflected or diffracted back towards the camera, but part of the light is reflected off this as though it's a flat mirror. And this is maybe 0.1% of light, but this is enough to collect for exposure metering. And so this is then collected with a mirror that sits, well, it sits above the grating in this orientation and put outside the vacuum vessel onto a detector there.
So it's not an overfilling. So it's not the overfilling factor that you use. It's really the
it's really
zero reflection.
We call this, so if these orders are order 35 to 95, this is order 0, the 0th order reflection.
Okay, thanks.
We still have some time for questions.
Hi Jake, nice talk. So sometimes you show these figures of the detector, and then you see that you have the 4 blazes of the 4 telescopes, and then the calibrator is on a different position on the detector. Does that mean that the light that comes from the Fabry-Perot instrument takes a different path through the instrument, and is that a problem for calibrating it? And is this also the case with Marvel?
So yes, indeed, it takes a slightly different path through the optics. It's also, so they're offset in this direction, but they also might be offset slightly, these fibers at the input in the wavelength direction. So indeed, we care about this. And this calibration trace here is really just the simultaneous reference. This is used to track drifts relative to other measurements. This we will not use for the wavelength calibration. For that, we really inject the wavelength calibrator light into our science fibers at each telescope to overcome exactly this.
All right, thank you.
Hey, you mentioned that the uniformity of your white light on the calibrator was like a big concern and such, but in practice, the starlight itself will be highly variable just because of atmospheric effects, difficulties keeping it centered on the guidance camera. So I guess, is that also going to be like, I mean, I guess that's the ideal, right? That the atmospheric effects and such are the leading role in your precision. But wouldn't those dominate any sort of calibration variability in basically all cases? Or am I misunderstanding?
The effects of Earth's atmosphere are not such a big contributor to our precision. Because we couple light into a fiber, optical fibers, they're not perfect, but they are very good at scrambling light, averaging it out over time. So what you get out the other end is very uniform. So it not only allows us to separate the spectrograph from the telescope, but also does this scrambling and acts as our slit. So the fiber really solves the atmospheric effects problem.
Okay, so it's really just the calibrated light that this non-uniformity becomes an issue.
Yeah, this here is really in wavelength direction that you get a shift. So the flux, the position, everything is highly uniform of this.
Hi Jake, nice talk. Could you go back to slide 36 where you were just now?
26, you said?
36.
36.
Yes. I was wondering here, because these orders are really quite close together, and then you're mashing in about 5 trays of light at the same time. Could it be that if you were to observe one really bright star and one really faint star, that there's some amount of bleeding from one star to the other? And is this something people who do scheduling should take into account?
Yeah, so it's definitely a concern. It's hard to tell on this scale, but we in fact have, I think we have 10 fully dark pixels between fibers nominally. Now, if you observe Betelgeuse and a bunch of magnitude 11 stars together, then yeah, the fiber with light from Betelgeuse in will saturate faster. So we have to have a shutter at the telescope end for each fiber in like each telescope to cut off this light so that everything is the same brightness on the detector in the end. That's the plan. Either that or always try and observe things that are basically the same brightness, or observe with all 4 telescopes the same target. So that's another mode of this that we expect is actually the most useful, because then you can really push to these dim targets.
There is still time for a very quick question, if somebody wants to ask. If not, let's thank Jake again. Thanks for coming. We still expect to see you all next week.